Hi, welcome back. Today's video is about the law of conservation of energy. It's a really important topic. It's one of the most important topics in physics, and what it says is that, I guess the way you heard it in elementary school is energy cannot be destroyed or created. Another way of looking at it is the energy that you have at the beginning of some interaction is equal to the energy that you have at the end of that interaction. It may not look the same, may not be in the same places, but it's still there. Okay, let's get going. So, in any isolated system, the total energy remains constant. Okay, isolated. I guess we need to know what that word means. Isolated is a system where there's no exchange with the environment. There's no change of mass. There's no forces coming in. There's no transfer of energy. So here we go. There's that basic definition from middle school. And now here's a picture that helps explain. We're interested in a system, and there's a boundary for the system. If that is an isolated or a closed system, there's no interaction between the environment and whatever's inside the system. Energy is conserved within the system. Okay. Now, here is a more formal description or equation of the law of conservation of energy. We have our system depicted by this blue oval, and it says that the energy in the system is equal to the potential energy plus the kinetic energy plus the internal energy. Well, what's internal energy? We know what those other two are. Well, internal energy is the energy of the mass and of the thermal energy, how warm it is. So we have to take that into account as well. Okay, so for our system, no mass can enter or leave, no energy can enter or leave, and then the energy of the system is conserved. That's one of the basic laws of the universe. Now, a particular type of energy is mechanical energy. And for our current study, we're mostly interested in mechanical energy. So we'll spend a little bit of time looking just at conservation of mechanical energy. So what this means is that within our system, only potential energy and kinetic energy are changing. And the sum of those two energies has to be a constant. So what that means is that if the potential energy goes up, the kinetic energy must go down. If the kinetic energy goes up, the potential energy must go down. If that's not true, something's broke. Maybe you got a Nobel Prize. I kind of doubt it, though, because it's the law. Now, more mathematical. Same thing. Mechanical energy is the sum of potential energy and kinetic energy, and it's a constant. Or the change in mechanical energy is equal to the change in potential energy plus the change in kinetic energy, and that sum is zero. The total change is zero. Okay, for gravity, the change in potential energy is mg times the height of the object in its final position minus mg times the height of the object in its initial location. Change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. Are we making any assumptions here? Well, yes, we are. We're making an assumption that there's no interaction with the environment. Now for springs, similar process. 1/2 kx squared minus 1/2 kx initial squared. That's the change in spring potential energy. Again, change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. And what's the assumption here? Well, again, there's no exchange with the environment. Okay, we're talking about a closed system. There's no interaction with the environment. There's no exchange of mass or exchange of energy. Another assumption that we're making is, with this particular set of equations, that our springs are ideal. And really the only kind of springs that we're going to deal with are ideal springs, with the exception of AP physics, which may have some non-ideal springs at certain times. Okay, next, let's look at a particular example of a pendulum. Pendulums and energy conservation. Well, because it's a closed system and we're assuming these are ideal pendulums, which means that there's no friction in the motion, there's no air resistance, and that the pendulum itself is massless and only the bob, the thing that's oscillating back and forth, has mass. So that's some assumptions that we're making. So in this case, mechanical energy is conserved, and it oscillates between kinetic energy and potential energy. At the top of the swing, it's all potential energy. As it drops, the potential energy is exchanged or turned into kinetic energy. And at the very bottom, it becomes all kinetic energy. It's at its lowest point. It has no, well, let's not say it has no potential energy, but all of the potential energy has now been transferred into or exchanged into kinetic energy. So here's a picto diagram of that. So the change in height is h. And kinetic energy plus potential energy, initial, is equal to kinetic energy plus potential energy, final. And that's good for any point in the swing. The mechanical energy, the total energy, is going to be a constant. Okay? So for any points, the energy at one point is equal to the energy at the other point. Okay? So at the maximum points, when the kinetic energy is maximum, it's equal to what the maximum potential energy will be. Okay? For the minimum and maximum points of the swing. So the potential energy at the highest point is equal to the kinetic energy at the lowest point. Now springs. They transform energy back and forth between kinetic and potential. In this case, when the spring is fully stretched or extended or compressed, when it's at its maximum excursion from the equilibrium point, the energy is all potential. It has momentarily stopped moving. When it passes through its equilibrium, it's going its fastest. That's when all of its energy is kinetic. And at all other points, it's a mixture. The total is a constant, but it's going to be different amounts of potential and kinetic. But when you add them together, it's going to equal either the maximum kinetic energy or the maximum potential energy. Okay, another pictograph. Okay, so there we've compressed our spring. It's in equilibrium. Now it's at its maximum. It's extended. So when it's compressed, it's all potential. When it's at equilibrium, it's all kinetic. And when it's extended, it's all potential. Okay, so there's the equation. The mechanical energy is a constant. The sum of kinetic and potential at one point is equal to the sum of kinetic and potential at another point, at any other point. Okay, so if we look at the maximum potential energy, that's equal to the maximum kinetic energy. They occur at different points. Maximum potential occurs when it's fully compressed or extended, and maximum kinetic occurs at the equilibrium point. Here's your multiple choice. Welcome back. Well, here's a problem for us. Here's a pendulum, and we want to know what the speed of the pendulum bob is at point B if it's released from rest at point A. Okay, let's talk about this for a couple of minutes. Well, when it's released from rest here, it has a certain amount of energy. It has potential energy, plus it might have kinetic energy. Well, in this case, it's at rest, so the kinetic energy is going to be 0. When it gets down here at the bottom, it could have potential energy, plus it has kinetic energy. Well, if we say that the potential energy here at the bottom is 0, all the energy is kinetic. So let's find the speed. Draw a little dotted line here. Now, we know that our energies are constant. The total mechanical energy is a constant. So that says at point A, we have m, g, h, and I'm going to say A, plus 1/2 m, v at A squared. And at point B, let's go ahead and say that's equal to E, the mechanical energy. At point B, we have m, g, h, b, the height at B, plus 1/2 m, v at B squared. And that's also equal to E. Now, let's go ahead, since they're both equal to E, that means that the energy at A is equal to the energy at B. So we have m, g, h at A plus 1/2 m, v, b, I'm sorry, I don't know why I just did that, v, velocity at A squared, is equal to m, g, h at B plus 1/2 m, v at B squared. Those are equal to each other. Well, at A, we said that the velocity was 0. It's momentarily at rest. So I'm going to notate that. And at B, we said that the height was 0. So the potential energy, gravitational potential energy at that point is 0. So that tells us that m, g, h, a, the height at A, is equal to 1/2 m, v at B squared. It's a good thing that the masses cancel out because it didn't tell you what it was. Well, now we can solve for the velocity at B. Doing the algebra, we have 2gha is equal to vb squared. Well, if we take the square root of both sides, that gives us the velocity at B is equal to the square root of 2gh. Well, that's great. I know everything here that I need to know. I know what 2 is, I know what g is, but I don't know what h is. Well, this distance here is h. Okay? So we have to figure out what h is. Well, this total distance is 1.5 meters. Okay? So what we have is this triangle that's been constructed, where this side is right here is 1.5 minus h. Well, what can I do with that? Well, I can use the properties of triangles, of right triangles, to find out what the length of this side is. Well, this is adjacent to the 40 degrees, so that tells me that we have cosine of 40 degrees is equal to the side 1.5 minus h over 1.5. And now we just need to solve for h. Okay, so after doing the math, we have 1.5 cosine 40 is equal to 1.5 minus h. So that tells me that h is equal to 1.5 minus 1.5 cosine of 40 degrees. Okay, so I can calculate h. I'll plug h into this equation and it will give me the velocity. So let's go ahead and pull up our handy dandy calculator, find out what h is equal to. Let's turn it on. So h is equal to 1.5 minus 1.5 times the cosine of 40 degrees. And that's equal to 0.35 meters. So h, this is 0.35 meters. So VB is equal to the square root of 2 times g, which is 9.8, times 0.35 meters. And let's see how fast it's going. Okay, so second square root 2 times 9.8 times 0.35. Close the parentheses. Enter. It is going a whopping 2.6 meters per second. Okay, so this works for any situation where you have an object that is exchanging its potential energy because of its height for its kinetic energy, as it moves down the hill. Okay, so let's see what's up next for you. Another example. Okay, we have a 0.21 kilogram apple falling from a tree to the ground, which is 4 meters below. Ignoring air resistance, determine the apple's gravitational potential energy, its kinetic energy, its total mechanical energy, when its height above the ground is each of the following: 4 meters, 2 meters, and 0 meters. Take ground level to be the point of zero potential energy. Okay, I don't think this is going to be too bad. Let's go ahead and draw a picture though. So we have our apple. I guess I better make that red since it's an apple. Whoa. And give it a leaf. Okay. And it is starting from 4 meters. And we want to know what's going on at 2 meters and at 0 meters. Okay, so I'm going to make a little table, U, K, and E. Okay, so U is M, G, H, and that's the height above 0. So if we have 0.21 kilograms times 9.8 meters per second squared times the height of 4, that gives us our potential energy. Well, it starts falling from rest, so kinetic energy is 0. Okay, let's go ahead and find out what our potential energy adds up to, or multiplies out to. 0.21 times 9.8 times 4. And that's equal to 7.56 joules. Okay, so total energy, E is equal to U plus K. Okay, so that would mean that U is 7.56 plus 0, which is 7.56 joules. Okay, down here at 2 meters, MGH is 0.21 times 9.8 times 2. Well, this is at the halfway point, so it has half the potential energy. So 7.56 divided by 2 is equal to 3.78 joules. So that's our potential energy. Well, if we decrease the potential energy by 3.78 joules, that means that the kinetic energy went up by 3.78 joules, leaving our total energy as 7.56 joules. Now, down here at the bottom, pretty easy to do. Potential energy is 0, because H is 0. Kinetic energy, well, if we have 7.56 total joules, mechanical energy, and there's 0 potential energy, that must mean that kinetic energy is now 7.56 joules. Okay? These tables are really helpful when you're doing this to keep track of the exchanges. Let's move on. Here's your free response question. Good luck. We'll see you next time.